Good evening, everyone. Thank you for joining into this third session. Again, our expert in the morning session, first session, Dr. D. Pamu, professor at IIT Guwahati. Good afternoon. He took the session, and now he is going to take another session in this one. And today morning, I didn't give introduction about the sir. Now I would like to give the introduction about Dr. D. Pamu sir. Sir is a professor at IIT Guwahati, and sir did his PhD from University of Central University Hyderabad, and he did MPhil, MSc, and BSc Physics from the Central University of Hyderabad, and he has got huge research experience. He was awarded Young Scientist Research Award from SERB, Science and Engineering Research Board, sponsored by Department of Science and Technology in 2012, and Young Scientist Research Award from Board of Research in Nuclear Science, GAE, in 2010, and also he has selected for the Dr. Kotare's postdoctoral fellowship scheme funded by UGC India. So there is much to say about sir, and we are so much privileged to have him with us. So now his area of research is nanomaterials, semiconductors, oxide thin films, bioceramics, ferroelectric and piezoelectrics, and high K and low loss materials. This is a brief introduction about our today's expert. I give this time to our expert sir this time. So we will have session from 3 to 4:30.
Dr. Srinivasarao, thank you for your introduction. Okay, very good afternoon to all of you. I thank all the organizers and the participants for giving me this opportunity. So today, the afternoon, we will look at some of the important applications of ceramics.
If it is possible, can you please switch on your video, sir? If it is possible, otherwise.
Yeah, actually, sometimes what happens is it will be unstable. It's not a problem for me. You know, if sometimes you may lose the signal, that's okay.
Yeah, due to bandwidth. Okay, sir, no problem.
So today we will speak about look at the ceramics and their applications in various sectors, especially because as we are looking at nano materials or the thin film coating, some of them, what we were discussing in the morning, we'll see some of the applications of them now. So that morning, what you have done, you will understand slightly better. Okay, so this is briefly I will introduce why we are particularly talking about a material and what is the importance of this material, all that we will see, and then we will see how a material is suitable for microwave applications. That's what we will try to see. The idea of choosing this topic is just that many times whenever I go for faculty development programs, mostly I see people who are doing PhD. So in that case, I thought it is a good idea, how we systematically study or take a material and how we systematically study in order to understand its properties, so that it will be very easy to get some publications out of it. Also, that we'll be able to understand the material technically, and the scientific community also will be benefited. That is what is the idea in choosing this particular material, where I will clearly, I'll basically put up how to study systematically a compound. Take a compound and you study its properties, so that you will understand what is the advantage of this study. Also, that you will be able to get a best out of the material that you are looking at. That is what is the idea in choosing that. So before I go into the composition of the material, as I told you in the previous slide, I'll introduce here a concept called a dielectric resonator. What do you mean by dielectric resonators? These are nothing but unmetallized objects, that means which are ceramics, which functions as a resonant device by means of reflections at the high dielectric and air interface. What is the meaning of it? We'll just see clearly. So it's basically the ceramic resonator is at the bottom. You see that when you put this material under the applied field, and one thing that we should always remember, we are talking about a resonator. So that means your cavity is at a resonating state, and under these conditions, you have to place your dielectric sample there. So if we look at a history of this, dielectric resonators, why we are talking about dielectric resonators now in the space or high power applications, because earlier people used to use the cavity resonators which are very bulky, and then people have started with the microstrip-line resonators. Again, they also could not suffice the main purpose, and whereas the dielectric resonators are the simplest samples. Like your dielectric resonator is like your paracetamol tablet, which functions very efficiently, and it's very less in size, weight, and very compactable, and you will see the device is much efficient. That is what is the importance of the dielectric resonators in microwave applications. And why we are particularly talking about microwaves is that microwave communication is that because anything that you look at, whether we talk about communication or any 5G technologies or anything you look at in these are all coming towards the high frequency terahertz applications. All these are all high frequency applications. Why? Because where you are having a lot of flexibility and the device response would be faster as you go higher and higher frequencies. That is where you see that everything is related to the high frequency related material applications. On top of it, you cannot use any material or every material in the microwave region for microwave applications. So material should have a dielectric constant where about greater than 30 at microwave frequencies. Whatever materials you study in general, by the dielectric constant decreases exponentially with increasing the frequency. That is where the high dielectric constant is required in order to minimize the size of the device. How it is related? If D is your device size, which is inversely proportional to the square root of epsilon r. What is the meaning of it? If I have a high dielectric constant, my device size will be much smaller. That is the meaning of it. High quality factor. What do I mean by high quality factor here? High quality factor means it is a low loss material. That means whatever field I apply to the material, that in the material the field is stored. That way it what is the meaning of it? Earlier, if you see, if you are above 40, you know that earlier, maybe if you have used the mobile phone before 2006 and 7, so you will know that earlier, the signal noise used to be a lot. While you are talking to somebody, you will sometimes you will listen to somebody's voice also. But those things will never occur nowadays because the quality of the signal and the the accuracy of the signal is much better if you have a very low loss samples. And temperature stability, TOF means temperature coefficient of resonant frequency. What is the meaning of it? Suppose I test the device at room temperature, which is suppose 30 degrees C. So same material, if I send it to space, these are all high frequency materials, and these materials are also being used in space. So in fact, these some of these materials we have developed to ISRO. Now there are there is another project which is happening with ISRO. We are preparing the material for this this purpose, resonator purpose and other circulator high frequency applications all are related to. So in that case, in the space your temperature is low. So as a result, what happens? These are all resonant devices. So the moment the variation in the temperature, there will be a drift in the resonant frequency. Suppose I have designed the satellite or the communication device at 8.5 gigahertz. The moment I take it to very low temperature, it may shift to 8.6 gigahertz or 8.4 gigahertz. There may not be 1 gigahertz variation, but there will be some, few hundreds of megahertz difference will be there, which will be, few megahertz or sometimes more deviation may come. In that case, it is dangerous because then the device will lose the communication from the earth. That is what happens. So in that context, the temperature stability should be stable. That means even though there is a slight variation in the temperature coefficient of resonant frequency, that means your resonant frequency should not drift. That is what is the character. So if I want to use any material for the microwave applications, these three characteristics are very important, if you want to say any material. So how do you, I said, the entire the in the resonator, the material should store the energy. How it stores the energy in a dielectric, which we know very well. It's a +2 physics. Generally, you would have studied. Lord Rayleigh showed that an infinitely long cylinder of a dielectric material can serve as a waveguide for electromagnetic waves if you feed them at a certain frequencies, critical frequencies. That is what you see arrows here. So these are all called there is a critical angle. So if you feed the electromagnetic radiation at a particular critical angle, what happens? This critical angle is nothing but theta c equal to sine inverse 1 by epsilon r. Once this condition is met, what happens? If your dielectric constant above 30, then the entire field will be reflecting within the sample itself. So that is where the entire signal is stored in the sample and it works as a perfect resonant device. That's what we see here. See, what are the applications of these dielectric resonators? You will use them as a filters, you will use them as oscillators, you will use them as an antenna. So of course, resonator is there. Here the resonator is there. Here also oscillator, you see there are resonators. Here also you see there is a resonator. So, they are used in radar detectors, cordless phones, global positioning systems, multiplexer, combiners, satellite and military communication system. And these are all, for space application, one type of device is, required because the frequency of operation are different for each, domain. For military communication, the frequency of operation is different. So, that's where you have to make multiple devices with different frequencies. And, this resonators can be of different shapes. You will see that, there will be even peculiar shapes also, depending on the nature of the application. So then we moved on to magnesium titanate, which is a sample we have chosen for microwave application. Why we have chosen this, my magnesium titanate material is that, as I told you, the requirements, if you want to use any material for microwave applications, what I told you, you need to have a very high dielectric constant at microwave frequencies, and you need to have a very low loss tangent and also temperature stability. So this material got these characteristics. So we thought it's a good material to develop. But the problem is that the material composition looks very simple. Simple magnesium oxide and titanium oxide, if I mix, I should get a magnesium titanate. But in general, in reality, it is not very straightforward to prepare this material. Why it is so? So that's what we have taken it as a challenge. Why it is so is that the moment we mix magnesium oxide and titanium dioxide, magnesium oxide is a hygroscopic material. The moment you mix with this thing, titanium oxide, instead of forming magnesium titanate directly, it will try to form a phase called Mg-Ta2O5. You will see as we move on. It by default it forms, and it is very difficult. That is the bad phase which we don't want to If that phase is present along with magnesium oxide, magnesium titanate, whatever are the good properties of this material, magnesium titanate, they will deteriorate very badly. So it is not very easy to center at a, you know, low temperature, and this centering temperature is very high. If you take it to high temperatures, instead of forming magnesium titanate, it will form MgTi2O5, which is again a dangerous thing. As a result, the properties decreases. That is the problem, fundamental problem with the material. So we thought, we took it as a challenge to, study and improve the properties of the material. So that is what we have chosen this material. So now just so now any material you choose, first thing what you need to do is you need to do a proper literature survey. Unless you do a proper literature survey, it is very difficult for us to choose, identify any material for the application. In that case, magnesium titanate we need to look at carefully. Here we have seen different literatures that is possible, and we try to compare the properties. And if we look at the centering temperature is more or less very high, and the properties are not very favorable. So that's where what we thought, we will try to bring the, want to give this material to any commercial applications. One thing that we should keep in mind is that the centering temperature or the processing temperature has to be minimal. Then only the industry will come forward. You may ask, sir, why it is so? Temperature, what is the point? See, if you want to center a sample at 1400 degrees C, you have to choose a furnace which will go up to 1500 degrees C. In the 1500 degrees C range, you will not be able to use a simple silicon carbide rod. If the furnace is made up with a simple silicon carbide rod, each rod costs you about, maybe good quality rod costs you about 3000. But if you have to use a 1500 degree furnace, there people use a molybdenum disilcide, element, heating element. Each molybdenum disilcide element costs you about $400 US. In a furnace, you have to have 6 of them. So you see that 2400 US are required to maintain a furnace. On the other hand, if I bring down the processing temperature to around 1000 degrees C, then the material will be, the processing will be very easy, the commercialization also very easy. So looking at this literature, we have chosen a method to prepare this material. So as I told you, the main disadvantage in preparing this material is, it requires a very high temperature. That is the problem. And also what we thought is that if we can identify a suitable method and add some, dopants to improve the properties, that is what we thought. And also that since we are making the material in the bulk form, we also want to see in thin film form how the material behaves like. Whether the properties, whatever we are talking in the bulk form, is it possible to prepare them in thin film form? Or is it possible to obtain the same properties in the thin film form? That is what is our challenge. So for this method, to do that, we have chosen a method called the polyol method. Basically, it's a chemical method. So what we did was, we have taken the powders, and these are the starting materials. And then by using NaOH and ethylene glycol, we have prepared the material. So in this case, what we have done is that in the magnesium test site, we have slightly doped a small amount of zirconium oxide, zirconium. That is the main thing that we have done in this study. So the powders which were obtained, we try to calcine the at 5 to 600 degrees C. What is the meaning of calcination when we talk about ceramic language? Calcination means we want the phase, exact phase to form. Suppose Suppose if I have taken a barium titanate material, barium carbonate plus titanium oxide should give me barium titanate plus carbon dioxide. So what is the meaning of calcination here? In the we will avoid all unnecessary reactants, like for example carbon dioxide and other things which are byproducts we don't want. We will avoid all that and we will only have the required phase possible in the calcination. Then these calcium powders, we take it to make them as a pellet or whatever shape you require for your application, and center them at higher temperatures in order to achieve a maximum density. What do I mean by maximum density? Why do I need a maximum density? Because for dielectric applications, if you don't get maximum density, what is remaining in the sample is porosity. This porosity means it will absorb moisture in the environment, and because the sample is porous, as a result, the moment I feed the signal, microwave signal, there will be huge amount of loss. That is where the quality factor will be poor then. That's where we have to have a high density. Secondly is that, excuse me. Secondly is that if you have a high densified sample, then you will have a very good mechanical strength. That is another advantage. So to do that, these are the conditions that we have optimized in order to get a good quality material. So now, since we are preparing the material from using a chemical technique, so what we have done is that whenever you prepare a nano powder, the good thing that you should do is the DSC TGA. What DSC TGA do? Here in the case of DSC TGA, it will tell you at what temperature you will get the exact phase formation. So here in this figure, you see that we have prepared the powder, and you see that here. So this is the DSC curve. See, at 547 degrees C, the phase formation is occurring, and which is a clear evidence for us. So that is where we have chosen the calcination temperature between 5 to 650 or 600. Why? Because of this. So we have optimized. We came to know that from DSC TGA plot, the phase formation is at 547 degrees C. And then accordingly, we have taken these powders and calcined at 500 degrees C, 550 degrees C, 600 degrees C, 650 degrees. So you see that at 550 degrees C, you got the required phase, but 500 degrees C, there is no phase. It's amorphous. The same thing we have also confirmed with the Raman. You may ask a question that, sir, why did you do Raman again here? Raman, actually in XRD, if there are small impurities, it is very difficult to notice or find out those impurities using X-ray diffraction. But if you take Raman, it will be very straightforward to find out, because Raman is very sensitive to the impurities also. That's where we try to confirm the our samples with the Raman, so that whatever study we are doing it is perfectly correct. And then, since we have prepared through the chemical process, so now you see that these particles, what is the particle size here? You see that we have taken a TEM, transmission electron microscope images, you see here. So we fix the 600 degrees C as a calcination temperature, and then we have taken the powder as a to look at the microstructure. You see, you have a very small grains, about 30 to 40 nanometers here, and then you see these are the lattice planes that are there between the so it's very easy to confirm crystal structure. And also this is called the SAT pattern, selected area of electron diffraction. So which shows that my sample is a crystalline sample. Top of it, you will see that these are the planes nicely appearing, and the spacing we can clearly find out. So which shows that whatever study you have confirmed with X-ray diffraction, you will be able to confirm with the transmission electron microscopy also. So that whenever we do a study, one thing we should always remember is that it is not that, okay, I have done X-ray studies, it is different. I have done microstructure, it is different. I have done thermal conductivity, it is different. I have done dielectric studies, it is different. It should not be. Whatever studies you are doing, you should be able to correlate with one another. Then only you will be able to write a good paper also. So you see that so far whatever we have done, we are able to correlate back. So we just have done a DSC TGA. From DSC TGA, we came to know that phase formation is occurring about 547 degrees. And then basing that, we have done the calcination with the 500, 550, 600, 650. And we found 600 degrees is to be safer side. We have taken 600 degree sample as optimized sample. And it is showing a nice crystallinity, and the whatever crystal structure is expected from the material, that is we confirmed from the X-ray diffraction. But to go further, we have gone with the TEM, where we will be able to see the microstructure. Not only the microstructure, we'll be able to clearly see the crystal structure what we have obtained through SEM through X-ray diffraction. Is it possible for us to do reconfirm from the TEM studies? So we could reconfirm that also. That way it is a very constructive study we have done. Then whenever we prepare nanoparticles, it is always good to study the optical band gap or absorption edge. So what we have done, as I told you, that we have doped with a different we have optimized the condition for zirconium 0.05 doping in the magnesium site. So these are the calcination temperatures, right? 550, 600, 650. 500 sample is amorphous, that's where we did not show. So we have seen that there is absorption edge, you can clearly see here. You see that sample calcined at 650 degrees C is showing a very high intense peak. Why it is so? Because it is the indication of the best crystallinity. That is what you can see here. So 650, the band gap is 3.82 electron volts, and 550 3.66 electron volts, and the 600 degrees C you got a 3.76 electron volts. So we are able to calculate the band gap using a torque expression. This is the torque expression. So what we have done is that we are able to get a variation in the band gap because that relates to the particle size. So since we have prepared very small particles, the quantum confinement effects are also will be possible in this case. Then what we have done is that, as I showed you in the literature survey, all these samples are centered at very high temperature, something like 1400 degrees. Since we have prepared nanoparticles, the smaller particles, we have centered them at a lower temperatures. So you see that 850 degrees C, 900 degrees C, 950 degrees C, and 1000 degrees C. You see that all the samples are, nicely crystalline, and these are centered samples. And again, to confirm whatever results we have obtained from TEM data, with the ritual refinement data, we have reconfirmed the lattice constant, the spacing, everything, again by doing the X-ray diffraction of the centered samples. Earlier we have done with the calcined samples. Now we are doing with the centered samples. Many times what we do is that we will take X-ray and say that phase is forming. That is what we will say one word. But if you do a ritual refinement, there are n number of YouTube videos are available. You can seeing them, you can easily fit the data, so that you will be able to further interpret your data in a qualitative manner. That is what we have done here. So now what we have done is that we have looked at from the ritual refinement data. Here we have shown here only one refinement, but we have done all the refinements and we have calculated the.
ये क्वेश्चन बताओ, आइडियल गैस परफेक्ट गैस में कन्वर्ट हो सकती है और परफेक्ट गैस आइडियल गैस में कन्वर्ट हो सकती है? आइडियल गैस परफेक्ट गैस में और परफेक्ट गैस आइडियल में।
Yeah, so we have confirmed the lattice parameters and lattice volume from the retrieval refinement data. And then you see the microstructure. So the microstructure of the samples are beautiful because they are highly densified samples.
जो आइडियल गैस वो परफेक्ट गैस बन सकती है.
Yeah, Dr. Srinivas, can you mute the other participants? There is noise.
आइडियल परफेक्ट ही होती है यार.
Yeah, so here we see that these are the different samples.
रियल गैस परफेक्ट गैस हो सकती है यार रियल गैस परफेक्ट गैस या परफेक्ट मतलब जो परफेक्ट गैस है वो रियल बन सकती है.
So here we see a uniform microstructure possible, and figure A, since it is sintered at low temperature,
होती है टेम्परेचर प्रेशर डिफरेंस पे, हाई टेम्परेचर लो प्रेशर पे. ठीक है.
Excuse me, can you mute all the participants?
ग्राफ दिखाते हैं 12th में तो है नहीं था थर्मोडायनेमिक्स.
Dr. Satish,
कल पूछो
Dr. Satish,
कल ये अपना नेट से कसमाना कंप्यूटर मिलता है.
Dr. Satish,
सब है फोन है फोन में है तो सब कुछ है.
Dr. Satish, can you mute your mic, please?
पानी क्वालिटी जा रहा है. आ जाओ.
So here we see the microstructure of the samples here. So at 850 there is still seem to be slight porosity, but as you increase the sintering temperature, you see that the packing is better, and then the uniform grain growth is better. So we have gotten a very good microstructure. What is the meaning of this uniform microstructure? It shows that, first of all, whenever we look at a microstructure, two things we need to observe. Is there any contrast between the grain and the grain boundary? If there is a contrast between a grain and grain boundary, that shows that there is a secondary phase. But in this case, these white spots you look at, these are not a contrast, this thing, because after polishing, these things have happened, and we have taken the EDAX and we have checked these are not any secondary phases. So we have confirmed the maximum density in the samples with the microstructure, and how we are able to achieve the maximum density is that because we have small initial particle sizes which will really enhance the densification, because smaller the particle size, higher the energy that is available for sintering. So it will enhance the grain growth much faster. As a result, at low temperature itself, you will be able to achieve the maximum density. But you look at in the literature, even the chemical processing methods are showing the sintering temperature of 1400 degrees. But in our case, you see that at 950 degrees C, we have gotten an excellent microstructure with a very good densification. That is what you need to notice here. And then we have you look at, we have calculated the relative density at 950 degrees C. We are able to achieve something like 97.5% of the density, and the grain size is about 3.34 microns. And the microwave dielectric properties we have measured at 9.5 gigahertz, which is mentioned here. These microwave dielectric properties are measured using a vector network analyzer and the Rupka calculator. This process is called, the method is called the Aki-Coleman method, where you will be able to measure the dielectric constant and the quality factor at a microwave frequency. So, and then you see that we have gotten a very good dielectric constant. So at the 1000 degrees C, even though grain size is larger, the density is smaller because there is kind of a abnormal grain growth. You see that this grain is bigger, but whereas other grains are smaller. So that would lead to the lower density. So that's where 950 degrees C is the optimal, densification centering method, optimal centering temperature, which gave us, good microstructure and uniform grain size and the good dielectric constant and the good quality factor also. That is 1,75,000 at a 9.5 gigahertz. So when we represent this thing, we will also multiply with the frequency. That is how terahertz we have put up. And then we want to see how the dielectric constant of the material changes with respect to frequency as a function of temperature. So you see that we have tried to measure the dielectric constant at different temperatures as a function of frequency. And you see that the loss tangent also we have measured. In this case, the loss tangent is of the order of -4. Whatever we are getting at the resonant method, we may not be able to get exactly that, because in the resonant method, you don't apply any electrode or anything. It's a pure material, you will place it. But at low frequencies, if you want to measure the dielectric properties, you will have to apply silver paint both the sides in order to make a parallel plate capacitor. That is how we measured the dielectric constant as a function of a temperature. Then, we have, since we have gotten a very good density, relative density, good dielectric constant, and we have gone to impedance spectroscopy. Why did I go to impedance spectroscopy? Because one way we are boasting that we have gotten a very good density, very good microstructure, which are evident, we are able to see with our eyes. But why did we do again impedance spectroscopy? Is that this impedance spectroscopy will give us in the second opinion, or it will try to help us to reconfirm whatever we are saying in the densification and microstructure, because this would give us what is the density, what is the resistance. If more resistance is there, that means the sample is more insulative. More insulative means more band gap. That is the meaning that we can understand. So for that, we have subjected the material with the temperature again, so that when we subject the material with temperature, then there may be some charge carriers which will get activated, and then they will try to conduct the conductivity. That's what we have seen. And we have measured further AC conductivity and try to measure what is the activation energy required to enhance if you want to break the material. So here you see that the activation energy at 2 megahertz is about a 3.6 electron volts, which is same as your optical band gap. If you see the optical band gap here, you see we are almost getting the same band gap. So what is the indication of that? The samples are highly densified, and these are all highly insulative, and they need a lot of energy to break the bonds in order to make the conductivity to happen. So that's where you see that one property is correlated with the other property, and you are back calculating and showing that what you have done is the perfect sample measurement. So that is how we are able to do the measurement. Whatever is being reported in the literature, compared to that, we have achieved a very good property. We have achieved very good properties, and they are also the temperature stable, and also they are centered at a very low temperature. So this paper we could able to publish in Journal of American Ceramic Society. So where it's one of the good impact paper. Why we could see, this is how you do a systematic study, and whatever is there in the literature, you compare the data with the existing literature, you will be able to do a very good publication. That is what we have done in the bulk part. Is it fine? Can I go ahead like this, or should I be a bit slow? Any audience? Any comments? Shall I go
Yes,
ahead?
sir. Go ahead, sir.
You are able to understand?
Yes, sir. Yes, sir.
Okay, thank you. Because I need your feedback, otherwise there is no point in just talking. So what we have done.
Continue, sir.
Yeah, okay. So what we have done with the bulk material, so we want to make a thin films of it and see how this material behaves. So for that purpose, we have prepared our own sputtering target in our lab. So we have the facilities, all the facilities possible to make a sputtering target. And then these thin films, because we have to have a parallel plate capacitor, so we have taken a platinum coated silicon samples for making a thin film capacitor. So these are the deposition conditions. Whatever morning I have shown you, there we have used the RF magnetron sputtering here. So the base pressure of the chamber is -6 millibar. The applied RF power is 80 watt. Deposition time 3 hours. Working pressure is 1 × 10⁻⁻2 millibar. And the substrate to target distance is about 4.5 centimeter. So now this is the before we deposit a material, we want to make sure that whether the parent material is behaving exactly what we wanted. So we have reconfirmed our target, exactly what we have done in the previous study. Is it the same or not? So we have done the ritual refinement and confirmed that our target is exactly coming. Then when we make a thin film, what we did was we have deposited on the silicon and amorphous SiO2. So this is top one is amorphous SiO2, that is more or less like quartz, and bottom one is the film that is deposited on a platinum silicon. And these samples we have annealed again at 600 degrees C, to induce the crystallinity in the sample. So you see that we have gotten a nice crystallinity in the samples, and these samples we further analyzed. If you see, there is a orientation factor of 104 plane and 110 plane. So if you look at here, so you see here, there is a competition. Here is a 104 plane and 110. 110 is smaller and again increasing. So that means by playing with you see 100% OMP means we have deposited the film in pure oxygen environment. 75% OMP means we have deposited at 75% of oxygen and 25% of argon. Here 0 OMP means we have deposited the film in a pure argon atmosphere. So when we go in the pure argon atmosphere, 104 plane is dominant, but in the pure oxygen atmosphere, 110 plane is dominant. That is what you will see even in both the cases. So that means the orientation of the film also you will be able to control by playing with the oxygen and argon percentages in the case of a thin film. That is what we have plotted here and shown it systematically. That's what we have done here. And you see that, you see this sample, these are all gas deposited samples, left hand side. After annealing, you see that the grain size is increasing. And these are all deposited on the quartz top and bottom. See, this is a 100% oxygen and 100% argon. You see that how the grain sizes are nicely distributed in the gas deposited film. So that's what you see. B is 100% oxygen and A is 100% argon. You see that argon has a large grain size compared to oxygen because argon ion has the large bombardment energy as compared to, because argon bombardment energy is higher, so the nucleation will be faster. So that is where the grain size is higher with the oxygen, argon. So you see that, and this we have done very systematically on platinum silicon. So you see that how nicely, uniformly we could grow nanoparticles, with the uniform particle sizes. That is how you will be able to play with it. So now After doing the microstructure, we want to understand what is the thickness of the film. Thickness of the film can be measured by transmittance spectra. So, this is done with the UV visible spectrophotometer, and you have taken the transmittance spectra. This is a as deposited film and a 600 annealed film. Annealed film is having a low transmittance because after annealing, your particle size will be larger. As a result, the light scattering will be more. So that's where the transmittance will be less. Similarly, these films on the right hand side, you see all the films we have shown there, and from this we have calculated the thickness of the film using these expressions. And see, these are the expressions being used to calculate the thickness of the film. And then we have calculated the refractive index, and then we have also calculated the packing density and porosity. Why we have done the refractive index, packing density, porosity? Refractive index and packing density are correlatable. That means if I have a highly densified film, my refractive index will be higher. The same thing, whether the same trend is coming with the packing density or not, we have checked it. And the porosity also. We have seen that at argon deposited films have a low porosity. That means they have a high refractive index. But pure oxygen films have a high porosity. They have a low refractive index. So we are able to reconfirm again back. That's what you see. And then band gap. If you see in the case of nanoparticles, the band gap, highest band gap is about 3.8 electron volts, 4.52 electron volts. You may ask, sir, why it is like that? Because these are all earlier particle size is same, more or less particle size is same. But here, since it is a thin film, the large surface to volume ratios are very evident in the case of thin film compared to the other particle shapes. So that's where the quantum confinement effect is very much evident. And you see that we are able to get a very large band gaps in the sample. So that means by playing with the thickness of the sample, you will be able to tune the band gap of the material off. And then similarly, we have studied the dielectric properties also. So the dielectric properties also coming as per the powder sample what we have prepared. But the loss tangents are slightly higher because in the case of thin films, your grain boundary is more. So more grain boundary means it will try to scatter the electromagnetic radiation. As a result, you will have a more loss tangent. That is obvious, that is expected. Otherwise, your dielectric constants are in the same range. And again, we have done the impedance spectroscopy here to find out whether what is the activation energy that is possible here. If we look at here, so the activation energy is 0.36. It is still higher because in this case the thickness of the film is very small. It's just a matter of 150 nanometers. So the thickness is smaller. That's where the activation energy is still whatever we have obtained. In this case, it is still 0.36. But in the case of bulk, we have seen the activation energy is 3.6 electron volts. But in this case, it is 0.6. In the case of bulk sample, the sample thickness is about 2.5 mm thickness, and diameter is about 8 mm. But here the thickness of the film is just 150 to 200 nanometers. That is where this will come down. And we have seen nice Nyquist plots are coming to understand. Based on this, we will be able to understand what is the grain and grain boundary contribution, because we have obtained very beautiful nanoparticles in the thin film from the AFM images. So that's where we have done the impedance spectroscopy. So we have clearly found out what is the grain resistance here and the grain boundary resistance from the each sample, and they are all dependent on the temperature. So this is how we could see that we have done the studies with the thin film. Whatever we have talked about the bulk, we could able to reach in the thin film also. That's what we have concluded. And these are the ball mill that we have used, and these are the dies to make the samples. This is the furnace, and this is the sputtering machine that we have used to deposit the thin film. And this is the X-ray diffractometer and Raman, then AFM. This is a SCM, and this is FESCM and SCM. And this is the impedance analyzer, and this is LCR meter, and this is the network analyzer we have used to make the samples for a characterization. And this is DSC TGA, and this is the Archimedes setup to measure the the density of the samples. So I will just wait here because the next part is different. So if you want to ask any queries related to this, you may ask here. Then I will move on to the next biomaterials section. So these are microwave materials section. So if you want to ask any question here, you please ask here. Then I'll move to the biomaterials.
Continue, sir.
Continue?
We are listening.
Okay. So you people are very good people. Okay. So we will move on. So this microwave materials is one of my interest. So this we have been doing it right from my student days. But recently we have started with biomaterials because here, even though we started biomaterials, this proposal came from a mechanical engineering faculty only, because whenever we talk about biomaterials, we think that physics and mechanical engineering has no relevance. Only it is a medical doctors or these people will do. But you will realize that with your to your surprise, it's unless a physicist and a mechanical engineer sit together and optimize the properties and give, no doctor or a biomedical engineering person will not be able to fabricate any of the implants. That is what we realized. Initially, when my friend asked me, we will do some biomaterials, I said, I am a physicist, why should I do biomaterials? But later we realized that it is the physicist and the mechanical engineer had to come together in order to make the biomedical devices. And I will show you some of the examples why it is important to understand electrical properties of a biomaterial as well as the mechanical properties of a biomaterial. With that, I will conclude. So for that purpose, we have chosen a hydroxyapatite as a material. You know that a hydroxyapatite is a well-known biomaterial. So any bioimplants that they do, most of them are made with a with the hydroxyapatite, because this hydroxyapatite you can normally extract in a natural resources like fish scales, mutton bones, chicken bones, eggshells. These are all natural samples, so biomaterials. From them also you can extract the hydroxyapatite. But in this case, in our case, we have synthetically prepared the chemical routes. Using a chemical route, we have prepared the biomaterial and trying to understand its properties. And there are well-known biomaterials possible. The fluoroapatite, chloroapatite, and hydroxyapatite are the famous biomaterials which are being used in the biomedical application. And why we are we have chosen a hydroxyapatite is that it is very much important, to deliver the drug to the cancerous cells, and also bone filling agents. Nowadays, if you see orthopedic or the dental applications, they badly need this thing, because we are giving this powder to some dentists, and we have given the technology transfer to one industry. So they are doing the tests. See, whenever you have a cavity, in the cavity they will put a cement that is nothing but hydroxyapatite. So we have optimized the process to generate a very good quality hydroxyapatite, and that will be the vendor is trying to get the market, and they are commercializing. We have already initiated the technology transfer, so the process is happening. It will go on. Okay, so we will see. So that is where it is very popular, and the orthopedic industry is very much important nowadays. You talk about any old people, everybody has to replace the knee joints. Lot of things are happening, and that is where this material, and how this material is fitted into the human this thing we will just see. See, our bones, made up of organic and inorganic materials. You see that inorganic part is hydroxyapatite water, and organic is the collagen. You see that this is the collagen triplex helix that is there in our body. Onto it you see the hydroxyapatite crystals. This is our human body. So you see that it's an inherent part of our body. And then if you see, hydroxyapatite is the main inorganic constant that makes about 50% of the bone tissue. Sorry, 65% of the bone tissue is made up of a hydroxyapatite. So it is very much important nowadays. You see that people are having a lot of issues, and that is where this hydroxyapatite is came into the picture. For example, if you look at the statistics from USA, what they have done is that they have done the hip replacement surgeries. In 1990, they have done about 1,01,840 hip joint replacements. But in 2000, they have done 1,52,000. 2030, it is projected as a 2,72,000. But the problem is that even after doing the hip replacement, then there is no guarantee that that person will be all right forever. So out of 1,44,000 surgeries that are done in 1997, 37,000 are revisited again, because beyond 15 years, that hip replacement will not work. So you have to have again new replacement. If there is a young patient, going twice through this replacement is a painful thing, and it is a very costly affair. So that's where we are trying to do these implants. How are we doing? Let us see. Why this the failure of implants occurs here? Because poor initial bone growth on the surface of the implants. As a result, they cannot integrate with the bone. Stress and strain imbalances between an implant and the surrounding tissue, that will lead to the loosening of the surface, and there will be a fracture, and ultimately he will have a lot of pain. Generally, a lot of wear comes. So once the wear is done too much, then your bone cell also will have a lot of damage. Ultimately, you will not be able to enjoy. So whatever replacement you have done. So in that context, the extensive research has shown that to succeed an implant as an implant, it has to be habitable for bone forming cells, so that they can synthesize a new bone tissue on the implant surface. That's where you will, if this happens, the problems that I have discussed in the top, they will not occur. So how did we do? So in this case, we have done, researchers have done this lot of effort trying to use cobalt, chromium alloys, titanium alloys for this. In the case of metals, in the case of ceramics, people are using titanium, hydroxyapatite, zirconia. Polymers, people are using this kind of thing. But bioceramics based, these replacements are much better. Why it is so? They are very good because of their good biocompatibility. Also, bones, bones also have a lot of nanostructures. All that, the interaction between the biomaterial and our body part will be much easier, and you will not have the pain, and our body also will not treat it as a foreign element. But the metals and these polymers also, they are biocompatible, but still there are issues. That's where people go for hydroxyapatite. So this is the crystal structure of the hydroxyapatite. This is the hexagonal crystal structure which is there. Of course, there is some issues with some researchers are unable to prove that it is a piezoelectric. Some people are saying it is not a piezoelectric, and so but we have done a thorough research on it, and we found that our material, what we are preparing in the lab, it is showing the piezoelectricity. But why piezoelectricity is important in this case? Piezoelectricity is important because the moment I replace a material in my body, if there is a piezoelectricity, it is good because the moment I apply a stress, whenever we please replace a replacement part in our body, then we have to move our body. When we move our body, there will be a strain. As a result, if the material is of piezoelectricity, then there will be a charge that is generated on the surface. This charge will interact with the blood plasma around the replacement, and it will try to heal the wound much faster. That's where piezoelectricity, having a piezoelectricity in biomaterials, which is important, and that is what we have also done that, and we found that result. So this is what I am just trying to emphasize. We could able to figure out that piezoelectric properties are very much important for better wound healing and a better compatibility in the material. So, and then along with the hydroxyapatite, we have also chosen a strontium titanate as a composite. Because why we have done a composite, you may ask, sir, already hydroxyapatite itself is a very complex material. Why did you add again strontium titanate? If you ask that question, strontium titanate is also biocompatible material. I will show you. And one more thing that is important in the wound healing is that if the dielectric constant is about 35 to 40 at a 10 kHz, then the wound healing will be much better. How that is, I will just tell you. As such, inherently, hydroxyapatite has a very low dielectric constant, something like 15. But we need at least 30 to 40 to have a very good wound healing. So for that purpose, we have chosen a strontium titanate to improve the dielectric properties that will ultimately help in the biomedical bio properties or wound healing, and we will show you how that is happening. So we have known that these are strontium titanate is a well-known studied material, so I don't want to put up here. So why we have chosen strontium titanate, because it has a very good dielectric properties. That's the reason we have chosen. And this combination we want to study. So how we have studied. So now you see that how the biomedical healing is happening. You see here, polymers or ceramics. What you do, you fabricate them with different structures here, fibers, membranes, all that, or scaffolds. Say with ceramics, we fabricate a scaffold, and these scaffolds, you see here, here your material is, your implant is there, and then to that you bring the applied field to close to that, to the, in the case of piezoelectric scaffolds. So the moment you bring them, when you fold this material, then there is a piezoelectricity, and you apply the field, then the wound healing is much faster. This is called the in vitro mechanical stimulation initiate piezo response. Otherwise, we can do like this also. You apply the field close to that. Here in the gap, the scaffold is being placed, and you apply the field. Then the piezoelectricity induces. As a result, the wound healing will be much faster. Now you know that, so far what we thought is that we are a physicist, why should we bother about? But you may ask, sir, you also said mechanical engineer is also required. The mechanical strength of the scaffold which we are going to place in this gap, all the mechanical properties we need to study, where the strength, other properties we need to study, mechanical stability, all that, because they are essential. Otherwise, what happens if the patient is heavy, your material just like that breaks, then there is no point in putting the scaffold or the joint replacement. That is where the mechanical engineer is required. So now this is the principle that I think you people know what is the piezoelectric effect and the converse piezoelectric effect. So here, if the patient has some problem here, this part is removed, and with the tissue engineering, you put a scaffold here, and then the healing process takes place faster. So we have tested with ABCD this sample how the cells are growing, biocells are growing. That we will show. Hepatite cells are growing. We'll show you. So as I told you, why we have chosen a strontium titanate, because it's already a biocompatible material and it is being used in the osteoporotic bone implants. So that's where we have chosen a STO in our study. So now we have started the preparation of this material, the combination of hydroxyapatite and ST, different percentages we have optimized, and then we try to study the properties here. You see that we are getting both the phases, hydroxyapatite and the strontium titanate, and there is one phase called the beta TCP phase, which is the which we don't want, that we will be able to eliminate soon, by optimizing the conditions. So we are able to see the composite here, biocomposite here, and we are able to clearly understand. And since beta TCP is there, we have tried to find out what is the percentage of beta TCP, and we found that in the case of the 20H 80S, that means 20% of hydroxyapatite and 80% of strontium titanate, there is no beta TCP. That means that is the best composition that we can have for the bio applications. So based on that, we have further continued our studies here. So we have also calculated the beta TCP, what is the percentage of beta TCP, and we have clearly figured out there is no beta TCP at 20H and 80S. So we have clearly found out that part. And then we have also done the Raman. So as I told you last time also, I have mentioned, in the X-ray diffraction, we are unable to find out a rotile TaO2, but in the Raman, we are able to find out rotile TaO2. Actually, initially we also did not do Raman, but our biomedical properties are improving drastically. And it's very interesting why these things are coming. Is there any secondary phase which is favorable to biomaterial is forming or not? So, to confirm that, we did Raman. Rotile TaO2 phase is a good phase to improve the bioactivity of the material. So that is where we are lucky to have in this combination again rotile TaO2, which will give us the best biomedical properties. That's what we have done here. So now we have taken the microstructures of these samples, and we try to find out the elemental composition, and we have done the particle size analysis. And whenever we prepare the hydroxyapatite, one thing that we always should remember is that calcium to phosphorus ratio should be always 1.67. If it is deviating from that, the material may not show a good biomedical properties. So that's where we have done the IDAX 2C, and we always get a more or less 1.6 as the Ca by P ratio, which is a good, which will exhibit a good biomedical properties. And as I told you, hydroxyapatite has a very low dielectric constant, but by adding the hydroxyapatite, ST, we could able to get a very good dielectric constant. So that's what we have done. We have done the temperature variation, and we have done the frequency variation in order to find the dielectric response. As I told you, more the dielectric constant, more charge storage is there, and if you pull the sample, you will induce the piezoelectricity. If there is a piezoelectricity, the wound healing is much better. That is where the electrical studies of the biomaterials are very much important. And now what we did was, so far I was saying hydroxyapatite is a biomaterial. How do I know it is compatible to the biomaterial? So we have done SBF, that is a stimulated body fluid, which is our blood plasma. I will show you in the next slide. So in that stimulated body fluid, we have placed the hydroxyapatite and the strontium, 20H and 80S samples. We have put up in the SBF, and we came to know that we are able to grow a nice, apatite. So these cauliflower structures are nothing but the apatite layer that is forming on the surface. So in SBF, what is happening is that the surfaces develop a negative charge which attracts the Ca+2 and PO4 3- ions from the solution. That helps helping nucleating the bone apatite. So these are structures are called bone apatite like structures. So this is what is the principle with that mechanism we have proposed, how the apatite is forming onto the surface. Whether you start with a hydroxyapatite sample or a strontium titanate samples, you are able to grow a very good apatite samples on the surface. And then we have done the protein absorption studies and MTTs analysis, which shows that what is the protein absorption studies on the surfaces of the prepared samples tells to understand the cell attachment, cell proliferation, migration, whether it is occurring or not, we will be able to figure out. And MTT, what is the meaning of it? Is carried out to determine cytotoxicity of the specimens under study. That also we'll be able to understand. It also gives us the vital information about the cell viability or metabolic activity that is required when we put an implant. That's what we see. In both the cases, we have seen 20H and 80S sample that is showing the best biomedical properties. That's what we could see here. And we have also done the TEM studies to see the growth of hydroxyapatite and the calcium strontium titanate. And this is the composite in the figure C. And we are able to figure out both hydroxyapatite as well as the strontium titanate. Also, we want to know the elemental distribution, whether the elements are both calcium phosphate or hydroxyapatite and strontium titanate, whether they have equally uniformly distributed across the sample. So we have done the elemental mapping to see the distribution of the elements. And then we have gone with the thin film depositions of the same material, whether so far in the case of bulk, we are talking about a replacement. But what you will do with the thin film? That's what we want to address. What is the problem is that whenever you put a knee joint replacement, which is a normal, which has become a very common surgery for everybody, old people, the moment you cross 45, the knee joint pains are much, and most of the times you see that you end up going going for the replacement. Yeah, so ultimately what is going to happen is that, on this titanium implants, if you coat hydroxyapatite, then it will be lifetime will be much faster. That is where the people have started coating the hydroxyapatite on the surface of the implants. Okay, so that is where the thin films are important, and we have been trying to do this hydroxyapatite coatings there. So now you see that these are all being used in various applications. So in that purpose, we have tried just a second. We have tried hydroxyapatite coatings on the different substrates, especially titanium implants, to understand the importance of the thin film coating on the titanium implants. For that, we have taken a titanium alloy, which is generally being used in the implants, and then we have subjected the thin film to that thin film to various biostudies to understand whether we are able to form the apatite, bone-like apatite. That is what our objective in doing this. So now we have done these things. I will get back to you. So as I was telling, when we look at what are the ions in the human blood plasma and the SBF, you see that sodium, potassium, magnesium, calcium, chlorium, sulfur, all that. If you look at the same as our body, that's where SBF is done taken as a standard to see whether a material is biocompatible or not. That is what we have done. And then we have done the X-ray diffraction in order to find out whether because these are all titanium rich, so samples we have taken, onto which only we will be able to deposit a thin film. So we have primarily characterized the implant material we have taken, and then that we have characterized both with the Raman and X-ray diffraction. And then you see that we have grown titanium. Onto the titanium we have done the SBF. You see the flower-like structure is forming. That means the cells can grow on the surface. That's what we have done, and to find out. And then we have made a thin film of it. See, 400 nanometers, 1000 nanometers, 3000 nanometers. To get a 3000 nanometers, we have deposited something like 48 hours continuously, because the thin film deposition will be very difficult with the hydroxyapatite because it gives a very low rate of deposition. Then we have gotten a very nice, beautiful film as the target, and then we have gone with the further studies. See, we have again calculated the refractive index and band gap. See, when we calculate the band gap, this material is highly insulative. What it tells that? So when I use it as a implant coating, then this material will not get worn out much faster. The more band gap means what is the indication? Material is more insulative. More insulative means what? More insulative means the material is hot enough. That is what from the mechanical studies also we could able to confirm. And then we have seen that the dielectric constant, you see the hydroxyapatite with the thickness, higher thickness, you are having a very good dielectric constant. So which will help the material, better wound healing in the process if we do the coatings. That's what we have done here. With respect to temperature also, we have studied why temperature variation is required, because when you do a implantation, and if there is any variation in the temperature, the property should not change. And we see the properties of the material are more or less stable, temperature. That's what we have figured out from this thing. And we have also found out the uniform grain structure, and we have done the EDAX analysis to find out HAP. We are getting in the thin film 1.58 Ca by P ratio, which is more or less closer even in the thin film. And we have done the contact angle measurement, nonlinear optical properties, to find out whether this film material is suitable for nonlinear optical applications, and it shows nonlinear response. And then we have gone with the contact angle measurements. Why did we go for contact angle measurement? Because when we place the implant in the body, whether it is a hydrophobic or hydrophilic, we need to know the nature of the material. Otherwise, what happens? You will not be able to use the material. So in this case, we figured out if the contact angle is greater than 90 degrees, and we found that it is a hydrophobic. That way, you can safely, put it in an implant. So we see that the contact angle is very high, and which shows the thin films are hydrophobic in nature. So these are some of the publications, and some of the recent publications also have come up in the scientific reports and all. And we have patented some of these works, whatever I have been talking to you. So that's where I am stopping here. So if you want to ask any queries, please. I am done with these presentations. Yeah.
Very
if you want-
informative session, sir. We enjoyed a lot. Thanks for your valuable session.
Thank you. So later, if you want to ask, want to do some work related to this or some measurements which are available in my lab, you may, contact. But you should not, many times, I give an opportunity, wherever I go. But you should not come in the peak this thing and say, sir, it's urgent, sir. Tomorrow is my submission. If the measurements are not done, it's not like that. If you have some leisure time where, especially we prefer people to come in summer, to where we may have some internships, to operate the instruments for you, all that. If you wish to do some measurements and do some collaborate, you don't need to do my collaboration. You can do your work. So instruments are free. If you are willing to do some of the measurements which are available in our laboratory, you are free to come and use. Okay.